Okay, so let's start this this new part of the answers. In fact, this last section it is long, right? So if you read this manual, this in this part, this section, we're going to learn to do two things. First of course, we are going to apply DFT, the theory you are applying, right? Plus, as you can see here, we are going to deal with surfaces, right? Surfaces are very important in technological applications, okay? So, in fact, any kind of technology basically is related with some surface properties, right? So, any kind of surface. In electronics, of course, you have to do interfaces, you know, for instance, for the silicon technology, you have to do interface and so on. That's the reason why silicon steel is, you know, the most. So steel is still it's the most used material in technological applications. Okay, so one thing you're going to learn here with me is how to build these surfaces. Okay, so right now I'm showing you the examples of two types of surfaces. This is, you know, here is the bulk, the unit cell of silicon. And what I'm going to teach you is how to clip. You know, this is the plane to clip and to create a surface. As you can see, you can clip in the crystal, you can clip in many indexes, right? So here's the 100. This is cubic XCC. 100 is equivalent to 1010 or 001. You know, this is exactly equivalent. Other surface, it is the 117, right? That is equivalent to the 101 or the 011, right? And the remaining one that I didn't show here is the 111, right? The 111 is a plane that covers, that connects all these corners here, and they have these three, let's say there are more indexes here, so we call these indexes, you know? So, but I just mentioned the most, let's say, most easy one to see, right? Later you will see that it's possible to put in different ways. So in all this tutorial, this last part of the tutorial, we're going to concentrate in the silicon 100. Okay. So we're going to use the FT, you know, to calculate the properties. But one thing extra is about, right? So other thing that we want to do is, if you want to observe surfaces, the directly, right, in real space, the only technique we have is either AFM or STM. So STM is a scanning tunnel microscopy, right? So this scanning tunnel microscopy is able to see actually the atomic structure. See this is, you know, the resolution is 5 nanometers, 50 angstrom, right? So you can see here, we call the experimentalists call this has a atomic resolution already, right? But the point is that this, I'm sorry. So the point is that this, first of all, the brights, the colors, right? The colors here, it's not here, but the bright it is, the closer to you. So basically, I'm just going to make a drawing here. Maybe I can draw here. Maybe we can do it, right? So let me do some drawing here. Hopefully it works. This way. So I'm going to draw a little bit, right? I think this process, I think it's possible to draw here. Right, so you see, hopefully. Ah, very good. So one thing is that you see this is dark, this is bright. So it means that this is in lower. So if you see the tip here, you see here the atoms. Here's a step here. So the tip comes here, right? So when the tip is close enough, some current will happen here. So there will be a current here. So this is a tunneling, which we call tunneling current. And depends on the voltage, right? So if you can apply a voltage here. So depending, if you have a negative bias, negative voltage, electrons will go from the occupied states, will go from here to the tip. Negative bias. So it means that the team is going to observe the occupied states of this material. Well, with positive bias, we do this the other opposite. We start to inject electrons in the system, so they have to occupy the talent electrons have to map the unoccupied states on the surface. So for negative bias, we observe the occupied. This is negative bias is the occupied states. Okay. You might ask, why is important to do this? Why is important to do this? Why is important to do this? And you have to check always the positive bias and negative bias. And you have to know that you will be able to, by the way, you are going to simulate this, right? For this, at the end, if you see the last part of the in the manual, you see these images, right? So you can generate this. Okay. So as I mentioned, this current indicated exponentially with C, right? C. So C is the distance between these here, right? So that's the reason why this current has this, it is powerful because this exponential decay allows this kind of experimental setup to start to see this kind of, this kind of details here. So this is the atomic scale. Remember, this is 50 amps from the final. So the experimentalists tell you, okay, I got this atomic scale resolution, but the problem is, where are the atoms, right? By intuition, sorry, by intuition, you might think that you can say that the closer it is the tip to the atoms, the brighter it is. So if I come here, you see, to keep the same current, I have to go down, right? You see, to keep the same Z. So that's the reason why what is plotted here is the position of the tip with respect to the observant. The closer is the tip to the observant, the brighter it is, the darker it is, lower it is. So it means that this image is giving information not only in X and Y position, but also in Z. Okay. So, and as I mentioned, this is the family of scan improved microscopy. So far, is the only technique we have in current technology that allow us to see directly atomic structures. If we're able to see atomic structure in real space, it's the only technique that also allow you to manipulate atom by atom any kind of atom. That's the best we have, right? So the dream is to build up a serial tip that is able to do very fast, manipulations. But of course, it's very complicated because how you can put so many tips in this region, right? Because you see it's a huge, it's a huge. The tip this region has like very large amount of atoms, and just because one of the atoms is protruding here, you see something like this, right? So you see the atoms like this, the atoms of the tip, right? So something like this. But because only one atom here, because of this atom is protruding. So this is thickly, this is sharp in cut. So because this atom is protruding, it's possible to have some sort of atomic resolution, right? That's the reason why it is a complete expertise of people how to prepare the tip, be able to observe it. Sometimes the experimentalists crash the tip with the sample to be able to have this kind of atomic resolution, right? So there is this is still a science under development. Other, I don't show here. They put a CO, let's say, they attach it with CO molecule here. And when they do this, they have even better resolution, right? Because they even imply other kind of, not only tunneling, but also the other kind of quantum behavior of this system, and that's it can improve this kind of resolution, right? But that's it. So the experimenters will come to you, and that will be your final project. I just tell you it's going to happen already. I will give you other image, testing image, and you have to tell me where exactly are the atoms, right? So if you are able to simulate this image, it's because you have you know exactly where are you comparing. So that's one of the most elegant ways to solve at the atomic scale the structures, the surfaces, is comparing your image with the experimental image and finding just by direct comparison you can infer where exactly the atoms are here. So let's say supposedly I know this is silicon, but where exactly are the silicon atoms, right? We cannot tell. The experimentals cannot tell you exactly where are the silicon atoms. And that's the reason why they need this kind of simulations. Now so in this field, in this area of research, the combination of theoretical simulation experiments are very important, right? So that's the reason why scientific work in this area needs the combination of both, right? Any questions here, please, somebody about this? So I just explained the technique, you know, the STM, and what is next is that we have to learn how to simulate this in the most optimal way. Questions here, please, somebody. No questions. I think that in some stage I gave it to you guys the STM, but anyways, for the chemist people, this is about STM. So if you like, I can pass more information on STM. That the basic, as I mentioned, this STM is because classically it is impossible for the electron to go from here to here, here, depending on the voltage, right? That's the reason there is a tunneling effect. And that effect, you know, was new before the development of STM, but in the 1986, the people in Zurich, in the IBM Zurich, they developed finally the functional STM, and they won Nobel Prize in Physics, right? Because of the discovering of this very important, very powerful techniques. Okay, so what we're going to do here is the following, right? So we're going to I'm going to teach you how to generate a force field on the fly. Okay, so what is this about? So in in DFT, well, let's tell the history, right? When before DFT, we have the Schrodinger equation, right? And to solve the Schrodinger equation it's only possible to do it numerically, right? And and Hartree showed us that you can solve the Schrodinger equation for many particles, but it still was incomplete, right? Because you need to find the correlation. So that's the reason why post Hartree-Fock they start to use these wave functions that also consider excitations and different configurations of the electronic structure of the material. And that lead to these very sophisticated methods, but unfortunately are very heavy. So you cannot deal with more than 10, let's say more than 10 atoms is almost impossible, right? So that's because the wave function is so heavy that no supercomputer can. So in the 60s, Watercombe presented DFT, right? And DFT is other way to try to get solution of the electronic structure, right? But in a much cheaper way and basically the same exact level as at least at the ground state, right? So in the 60s and 60s, 70s, they call DFT as the sledgehammer, right? So imagine that. Now I can compute systems of hundreds, thousands, let's say, even right now, even thousands of atoms at the level of the Schrodinger equation. That's impressive, right? It's like to make tricks. In fact, it's just, it's an algorithm that allows us to do this. But if you want to go higher, let's say you want to scale up or you want to investigate the behavior of materials in a very long time, right? Or you want to see, or you want to study more than 10,000 of atoms at the level of this method, that is impossible. So today is impossible, right? So I remember one case of one student. She already graduated, right? And she was studying this metal organic frameworks. So inside of the project, they wanted to know the new structure, the metal organic frameworks is a growing field of areas of many every day the groups are synthesizing and finding new structures with interesting properties, right? So that is this avenue is very interesting. If you are interested, I strongly recommend to look on this because there are so many things to do research there. So I remember that she created a Hermov, big structure, and sent it to the supercomputer, and the calculation collapsed. She overloaded the supercomputer, and that was it, So it means that it was not possible to do the calculation she was trying to. It was a system, I think it was a system of something like 1,000 or something else. So it was not possible to go at the level that it was. Okay. So that's it, So it means that we cannot go at this level to compute properties. But the point is that later, during these last years, the machine, remember the four paradigm, right? The four paradigm is, you're part of these four paradigms. Is this machine learning, artificial intelligence. So what they did here, the group that developed this program is that they start to include some routines of machine learning in maths. What is the aim? The aim is to try to give predictions on these systems, but faster. How? Is creating dedicated force fields, right? Force fields, there are force fields since the beginning of the atomic studies in the history of the 30s. The most famous force field is the Lennard-Jones, right? And it's still is applied in many studies also. But unfortunately, these kind of force fields are too generic and might lead. Remember, I was saying that the limitations of these empirical methods is that you need to check and be careful that what kind of predictions you can get from the force fields, and that is very tricky, right? If you want to generate your force fields in the classical way, it's trial and error, and it's very, it's a complete field, expertise. Yeah, in fact, I've seen this kind of production of force fields, and it's very, very demanding, right? So this is a new kid on the block, right? This generation of force fields based directly in DFT. So look this, it has no dependent experiments, depends only completely in DFT. Why is it important? Because remember, DFT right now is able to provide predictions that you can, if it's a new material, you can synthesize in real nature. That's the reason why it's so important. So as you can see, some experts tell that this is the newest sledge hammer, right? So it's amazing, right? So when I went to Range, this field of DFT was still, on development, right? It was not even a book was already. I remember when I was finishing my PhD, I found finally a book on DFT, right? So copy I gave it to you, right? This is Richard Martin. Electronic structured calculations, right? That was one of the books I remember that was, I wish I had that book before, but that's it. Okay, so as you can see, this nowadays, when I was your age, it was impossible to think a system even born with 100 atoms was, you need to have a supercomputer to run that. Nowadays, how this evolved. Right now we can do the hands-on session in your laptop with systems that 20 years, let's say 10 or 20 years ago was, no, 10 years ago was alright, but 20 years ago was almost unthinkable, was too long to do. Okay, so right now you have a new method, right, that will allow you to see that it will be possible to simulate at the same level of prediction. That's very important. For big systems, using this kind of, right? So that's it. It is open up, again, a new interesting field of research in a new method of research in many field areas, right? because we need, the power of these kind of methods is prediction, right? So we can emulate some experiments of certain conditions, and you can give a fundamental answer, right? So there it is. Of course, this is, for instance, right now we're going to do some simulation on silicon. First of all, we are going to start training this force field in the bulk that we know, right? So we computed already a bulk in the previous sections. Right now, we're going to do a molecular dynamics. By the way, all molecular dynamics. If you want to understand for instance, one of the applications of this kind of machine learning is to understand the phase transition of materials, To study phase transitions, given by the temperature of materials is unthinkable yet, because it may take years to do a very careful simulation to, let's say, to bring the material from, let's say, 50 Kelvin to 800 Kelvin. So if you want to do properly, I don't know how many years we will need to do this, right? So that's the reason why with this, you're going to see that this is very cheap, very fast, and is the accuracy and the results, how reliable are the results are very important. Okay. So just to show you something, the INCAR file now looks something like this. Just I'm going to show you something that you're going to see the input files are already given, right? So as you can see this, I'm going to do like this, okay? As you can see, this is the typical INCAR file to do to train the force field. By the way, I forgot about the force field, right? What we fit, right? The force field has important parameters. First of all, the force field tries to divide the energy, right? So this is important. So the energy in the force field, remember, in the energy, you cannot split the energy. Remember, you cannot split the wave function because, the wave function is the whole unified thing. In DFT, we are able to use independent electric fiction, but we have still the energy. In force field, the energy is a combination, right? Different terms is by of each element. Let's say, I don't know, I'm going to put element right? So this is the total energy is a sum of in this kind of simulations. This is trying to find the energy in different contribution of many parts. That is not possible, right? But this is an approximation. That's the reason why it's just an approximation, but we try to make it with certain errors and so on. So it is good enough, right? So based on the real calculations of the what is the first thing. Second thing that is this, remember, this machine learning, what is doing? Machine learning is like fitting in a multi-dimensional variable. That is a machine learning. So we're going to train some model in many dimensions, let's say, because we consider energies, forces, and stress. We have three things, right? So it means that with this machine learning, we will be able to find structures, we will be able to find forces, we will be able to find the stress, and that's it. If you ask me, can I predict the electronic structure of some material using machine learning? No, you cannot. Because remember, this is the force field, the concept of force field is this, right? So the interaction between two electrons, right? So two atoms, A and B, in quantum mechanics, due to this interaction of the electronic the electrons. In the force fields, we simplify like this: A, B, with a spring. That is the simplification. Of course, this spring has many parameters based on what? On the electronic structure, right? So that's it. So basically, in force field, we strip off all the properties of the electrons and we parameterize this with the springs. That's it, right? So that is doing this. Is doing this force field. And my force field is going to give me predictions about everything: energy, forces, and stress. So my training will be based on the trios. So I repeat again, it's not possible to get any kind of electronic structure. But let's suppose that you have a system. I am not going to do this with you guys, but no, in fact, we are going to do this, right? So what we are going to do is, just to tell you this, is we're going to try to get what is the atomic structure of this structure, of this. We are going to try to compute or to what is this? We're going to try to get the atomic structure of this surface using force fields, using machine learning. And after, when we get the structure, we do a next step. We do a typical static calculation of the electronic structure, and we can get back the electron. Okay, so it's not possible to get right away the electronic structure just from the force field or the machine learning. Machine learning only allows us to find very quickly what will be the configuration of this atomic structure on the best level, and after that you can plug into the past and we go. Other thing could be like this, right? Sometimes we want to get the best guess of some structure, and after that what we do is do a final is a very quick relaxation with full DFT, and we get the electron. So we have two ways, right? So we are going to do that, right? So first to get the what is the reconstruction of the surface, and after that we have to compute again the electronic structure from the relaxed atomic structure that we get from machine learning and get this system. To get this system images, you have the electronic structure. Okay, so that is basically in general the what is doing these calculations, right? And what is doing this machine learning. Okay, so okay, so please, I'm going to pause here my recording before I give some instructions. Okay, 1 second. Okay, so please, first thing is go to the decompress this file. The file that I shared to you guys, this. Right? You just compress this. Okay. This part 8, ml.zip. So this ML stands for machine learning. Okay, so decompress this, please. And that's it. Okay. So this is, as you can see, this is more complete DFT. Right? Now here we have to follow slowly, right? So do not panic. It's not big deal. So we're going to do in order, right? Okay, so everyone please to here. So because we're going to follow what is saying in the manual, right? So the manual says go to the directory part 8 silicon 110. So here is part 8. So in this case, it's part 8. I just upgraded this to ML. And all the following. So in those calculations, we are going to use this PAWPV. So this, remember, we compute the ground state of silicon FCC with two functions, right? With PVE and PVE solve. So we are going to use PVE. So why we use this? Because very practical, functional. It's very easy to do calculation with this, and is one of the most used functionals right now. Right, this is a function that give you a good predictions to start with, right? So as I mentioned, that to generate the force field based on machine learning, we're going to run NPT molecular dynamics. So NPT means that we're going to allow to change, if we say NPT means that we're allowed to change the shape of the cell and also the temperature, right? Well, this is we're going to keep certain temperature, and we allow to the system to change the shape, right? So that is the thing, okay? So We are going to use the script ml.sh. So let's check what is ml. So this is the first script that we're going to use is this one, please. ml.sh. You see? Let's see what this is about. Here it is, okay? So please check that you have everything here. In my case, I'm going to use force equal to, I'm going to use only four force in my case, only in my case, please. In your case, please keep it using the maximum because this is a long calculation and in my case, I want to run, in the lowest, not too fast, but to be in the smallest, to know how long do you need to finish this, or it's going to be a little bit long. Okay, as you can see here, this is the input parameters. So the first step that this script is doing is we're going to create a directory called ml. So inside of this folder part 8 will be a other directory or other folder will call ml. And as you can see, it's going to copy the postcard. So we're going to check this. What is this 2 by 2 by 2? We will check in a moment. The incar ml, you see. The icons, we're going to see what is icons and key points ml. And the PA, you see, automatically is going to copy this PAW podcast file to podcast file. So basically, we will have we have only to run the script, but we have to understand what is this. Okay. The output will be saved in this ML, and after that, look this, we're going to save the steps and the times. So we're going to extract the step and the time in results.ml.dat. So we're going to use this, okay? And we're going to move up then this, okay? So first thing is look this, I'm going to open the postcard. So I'm going to investigate what is this postcard 2 by 2 by 2 and the incar ML and incons. Okay, let's check all the files. First of all, the postcard. So I'm going to open a terminal here. I'm going to open a terminal here, please. I'm going to open. I'm going to increase the size. Sorry, guys. Settings. Okay, change. Where is this? Line spacing. Is better this? Second. Is this better, Danny? You're happy with the size of this? Okay. So I'm going to get in this, okay? So I'm going to start with this. I'm going to open my terminal there. Okay, so there it is, my terminal. So first of all, what is this? Let's see what is this postcard. So with ASER, right? ASER USB postcard 2 by 2 by 2. As you can see, this postcard 2 by 2 by 2 is this. You see? Is this, right? From where I got this postcard file, you got from the structure, from the optimal structure of silicon FCC expanded in 2 by 2 by 2 or two times in all directions, right? So we have this. Why I'm doing this? Why you expand this it's very important in machine learning to have a big cell because of the phonons, right? So if you constrain the system to the unit cell, some phonons won't be included, will be frustrated because of the size of the supercell. That's the reason we increase at least 2 by 2 by 2 to include the more phonons, and then my description will be better, for my force field. That's the reason why we do this, okay? Okay, so accordingly, let me see this, the postcard file, the incar ml. So let's see what is this incar ml here. You see? Let's see what is this incar ml here. See this? There it is. The incar ml is actually presented in the manual itself. So here we switch off the symmetry. Why we switch off the symmetry? Because we want the relaxation has to be free, right? So the atoms should move anywhere
with no symmetry in position of symmetry. You see the algorithm, we use this EVW, so we include some van der Waals contributions on the structure, okay? Because at the end we are going to use on surfaces. So surfaces, the interaction on surfaces, you have to include some van der Waals interaction. In this case, smear is one. Why? Because we are going to have a metal-like. Sometimes the system will behave as a metal, depends on the structure. So that's the reason we use this. This is just to improve the speed of the calculation, no worries. Remember the cutoff energy was 400. And now we put a diff, the total energy, the convergence is 10 to the minus 6. By default, it's 10 to the is 10 to the minus 5, but we are going to increase a little bit. We are not going to save the wave functions and also the charge density, and we are going to run in reciprocal space. So this is very accurate calculation. And look here, this is the molecular dynamics, right? So when we put ivory on 0, it means that we are going to do MD. Okay? Look this. We are going to do 10,000 steps of remember in the since this molecular dynamics is going to use a Newtonian-like model, right? So we need the delta t is the change the increment of time, and also what we are going to need how many, right? How many steps? We are going to use 10,000 steps. We're going to do this, okay? This is just the algorithms we include for the NPT simulations. And the temperature, we're going to use 400 Kelvin. So we're going to do a molecular dynamics during 400 Kelvin, right? 400 Kelvin for 10,000 steps. The first steps, you're going to see clearly, the first steps sometimes are just equilibration, right? So the beginning is a little bit fake because we distribute the velocities or based on this temperature using the Boltzmann distribution, right? And after that, I will allow the system to to evolve in that temperature. And later, once the energy is equilibrated, from that above, that we can get the proper predictions. Okay. IC3 equal to 3 means that we allow the system to change not only the internal coordinates but also the volume. So that's the reason this is okay. And here it is, machine learning. This is the parameters here that allow us to train my field. So here is we switch on the machine learning, right? If you don't switch on the machine learning, to do 10,000 steps, I don't know how many hours will take it. Okay, so here we can do this. We can see that we will be able to do it in a reasonable time. And this is, the important here is this, the MLLMFF. True, it means that it will generate the machine, we will train the machine learning and so on. And always, please try to get this random seed, right? That will help us to reproduce the results, right? And so on. Okay? So that is the Inker file. Let me see now the K points. The K points, remember, was 999 for the primitive cell. So the K points here for the LMML, where is the K points ML? Here it is. Here it is, right? It's 2 by 2 by 2. Okay, so this is the K points we're going to use. What else? What else? We have the podcast file. The podcast file is the same we used before for the silicon, right? So this, as you can see, it is PVE. This is for hydrogen. Sorry, we're going to use for the silicon is here. As you can see, we're using the typical 4 electrons, valence electrons, and so on. Okay. So that's it. You don't have to manipulate anything, just to remember what that. Remember, you have to have at least 4 files. Incar, Oscar, Incar, Oscar, K points. But the icons, what is this? The icons, sorry. This is telling me to extract information on my MD simulator.
So basically, I'm going to extract information about the energy. So you can check this in the map. Energy, we're going to extract information about the lattice parameters. So, and the volume. So with that, we can see with how it's changing the volume changing the volume and the energy in my system, right? That is very important. Okay. There it is. So we are ready to do the calculation, okay? So as I mentioned, once it is finished, right? It will generate a folder called ML, right? So as you can see, this folder, this will create this ML. So as soon as it starts, we'll create a folder ML, and after we'll create this, we'll import and copy these files, and we'll run this. So output ML will be always updated. But after, when it finishes, you're going to get these files, ML log file, and many other files with ML like this, but the log file and MLFFN. This MLFFN is the actual force field that we're going to use later. Okay, so later we're going to run to generate this. Okay, so let's start please with the calculation. Okay, so please do ls and run it. We're going to run ml.sh. Right. So let's run it. I'm going to leave it in the if you put ant will be in the background, so you can still use this window. But I'm going to leave it like this. Okay. So it means that if I press enter, won't be able to run this to use this terminal, but I can check this again here, right? So I open two terminals. So let's say I'm going to open a new terminal here. So later we are going to see this produce this ML. Okay, so let's run it this. Okay, don't worry about this because it erased a wavecard that was ML and look this here. There is an ML, you see, and tile. So is this okay? And tile minus F opens. You see, this is running here. Okay. So I'm going to pause this. This is going to take a long time, please. I'm going to pause this.